Okay, let's unpack this. You're starting your day, and almost without thinking, a few key questions pop into your head, right?
Mm-hmm. Like, where do I need to go?
Exactly. Where do you need to be? What time is it so you're not running late?
Uh-huh.
And of course, how cold is it out there? So you know what layers to grab.
Yeah, the essentials. We take these measurements for granted distance, time, they organize our lives.
But it's that third one, temperature, that I find particularly fascinating. It's such a subtle thing, isn't it? Yet it underpins so much.
It's remarkable, really. You have an intuitive sense of hot and cold from, well, day one.
Sure.
But the ability to actually measure temperature accurately, that's relatively recent, only a few hundred years.
And understanding what it is, that it's molecules whizzing around.
Even more modern, the kinetic energy idea, yeah.
Yeah.
Much newer than, say, clocks or maps.
Exactly. We've had ways to gauge distance and track time for millennia, but really getting a precise handle on temperature,
Mm,
that's a fairly new achievement.
it is.
And that's really the mission of this deep dive for you. We're going to explore the profound significance of temperature. We're drawing from Gino Segré's book, A Matter of Degrees.
It's a great source because temperature, it turns out, unlocks so many secrets.
It really does. About our past, our present, even the future, from, how our bodies work all the way out to the scale of the cosmos. It's incredible.
It touches everything. It's not just about grabbing a jacket. It's fundamental to biology, civilization, physics, Earth's history, even stars. It's the key.
Let's start close to home then. Our own bodies. You and I, all mammals, birds too. We share this pretty amazing thing of keeping a constant internal temperature.
Homeothermy. We often say warm-blooded, but yeah, homeotherm is the scientific term.
And it contrasts sharply with most other animals, right? The poikilotherms.
Totally. Think of a lizard basking, like you said. Its temperature just follows the environment. Homeothermy is demanding.
How so?
Well, it needs a more complex brain, a much higher metabolism to generate that internal heat. And then you need sophisticated cooling systems too.
Right, because you can overheat.
Exactly. It's an evolutionary path only a small fraction of species took. Which tells you something, doesn't it? There must have been strong pressure favoring this energy-hungry strategy.
So why did it evolve? What's the thinking there?
Well, one key idea links it to moving onto land. Water temperatures are generally more stable.
Okay.
But on land, big swings. Plus, life got more complex. You needed faster, more intricate decisions.
And a warm, stable brain is better for that.
Seems like it. Much better for rapid processing. And there's another thing. Chemical reactions.
They speed up with heat.
Generally, yes. Higher temps mean faster reactions, more activity. Up to a point, obviously. For mammals and birds, that sweet spot seems to be around 100 degrees Fahrenheit, give or take.
It's amazing how precisely it's regulated.
Oh, absolutely. And sometimes in ways you might not expect.
Like what?
Well, think about male anatomy, testicles and external sacs. Why?
Ah, I've always wondered that.
It's because sperm production works best slightly cooler than core body temperature. That's how sensitive some processes are to temperature. Fine-tuning.
Wow. So how do our bodies manage this? Especially when we're, exercising and generating loads of heat.
Two main ways. Panting and sweating. Birds, some mammals, they pant. Evaporative cooling from the airways.
Okay.
There's this amazing example, the East African gazelle, running flat out, generating huge heat,
Right.
but its brain stays cooler. The rapid breathing cools the blood going to the brain. Pretty neat biological engineering.
And then there's us, humans. Not much hair, relatively speaking.
But millions of sweat glands, about 2 million all over, controlled by the hypothalamus in the brain.
And they release salty fluid. Sweat. Feels gross sometimes, but
Incredibly efficient cooling, especially when your metabolism ramps up. Exercise, for instance.
think about Tour de France cyclists. That's extreme.
It really is. Something like 75% of the energy they burn just becomes heat.
75%.
Yeah.
How do they cope?
They have to evaporate an insane amount of water, maybe 10 quarts a day through sweat.
10 quarts.
Yeah, constant drinking. And they rely on the airflow from riding fast to help that evaporation. Without that breeze, they'd overheat incredibly quickly, even being super fit.
So what about living in deserts? Humans and animals must have special tricks.
They do. Humans adapted to deserts often sweat less, and their sweat is less salty. Conserves minerals, makes them thirstier, so they drink more when water is around.
Smart. And camels. They're the icons of desert survival.
Oh, camels are masters.
Yeah.
They can drink huge amounts quickly, then manage their temperature based on hydration.
Wow.
When water's scarce, they let their body temperature fluctuate much more. Heat up a lot during the day, then radiate that heat away at night. Minimizes water loss from sweating. It's all about survival.
It's interesting. Even centuries ago, people noticed evaporation cools things. Ben Franklin, right?
Yeah, Franklin was curious about everything. He did experiments with ether on a thermometer, showed how quickly it cooled as the ether evaporated.
And desert travelers knew to use porous pots for water, keeping it cooler. Basic physics in action.
Exactly. Now, what about water itself, being in water?
Right. Evaporation doesn't work the same way then?
Yeah.
Think of Lynn Cox swimming in the Bering Strait. That water was, what, 44 degrees Fahrenheit?
Practically ice water. How is that even possible for a human?
Good question. How do seals manage it?
Well, seal blubber isn't just insulation like a wetsuit. It's active. It has blood vessels. They can constrict or dilate those vessels, control heat loss precisely. Depends if they're in cold water, warm water, exercising, basking. It's a dynamic thermal regulator. Humans shiver, constrict blood vessels too, but it's not the same specialized system.
And staying warm in extreme cold air, like those early South Pole explorers. Scott's expedition.
A brutal lesson. Frozen clothing was a huge danger. The key, they tragically learned, is trapping air.
Because air is a good insulator.
A very poor conductor, which makes it a great insulator, yeah.
Yeah.
Still air, multiple layers of clothing trap pockets of that warm air near your body, stops it being blown away. Down jackets work on that principle.
Okay, let's switch gears a bit. Fever. You'd think with modern medicine, we'd always know why someone has a fever.
You'd think so, wouldn't you? But it's often tricky. There's even a classification. Fever of unknown origin, or FUO.
What qualifies for that?
It generally means a fever lasting at least 3 weeks, hitting 101 Fahrenheit or higher, and doctors can't find the cause after a week or more of thorough hospital investigation. It happens.
Wow. Before modern science, what did people even do for fevers?
A lot of folklore, trial and error. Quinine from cinchona bark was known to work for malaria, which often causes fever.
And aspirin.
Came later, derived from willowbrook compounds. But how it actually worked inhibiting prostaglandins to reduce fever and inflammation that wasn't figured out until the 1970s. John Vane won a Nobel for that.
So fever is often the body fighting something, right? Invaders.
Often, yes. It's a response to microorganisms, bacteria, viruses. They disrupt the body's equilibrium. And remember the whole germ theory of disease. Pasteur's work. That's only about 150 years old.
Relatively recent, yeah. Before that, surgery was incredibly risky.
Hugely. Infections were rampant without sterile environments. Pasteur showed how these invisible microbes spread through contamination.
And not all bacteria are bad, are they? E. coli, for example.
Exactly. E. coli is normal, even helpful in our gut, but get it in the wrong place, like the urinary tract infection.
And then there are the really nasty strains.
Like E. coli 0157-6im, from contaminated food, often undercooked ground beef, causes severe illness.
But easily killed by heat, thankfully.
Yep. Cook that hamburger to 160 Fahrenheit internal temp for just 15 seconds, and it's safe. Simple temperature control, huge health impact.
It's interesting, this link between infection and temperature. Does seeking warmth when sick happen in other animals?
Oh, absolutely. It seems quite universal. Even insects do it. Fruit flies, when infected, will actively move to warmer spots.
Really? Fruit flies?
Yeah. Scientists have even used those weird giant chromosomes in their salivary glands, polytene chromosomes, to study the genetics of this immune response in detail. It connects back to how organisms react to temperature changes during infection.
Okay, let's zoom out again. Human civilization. Stone Age, Bronze Age, Iron Age.
A common way to frame history, and it's directly tied to fire, isn't it?
Absolutely. Each age represents a leap in controlling temperature. The Iron Age needed fires reaching, what, 2,000, 2,500 degrees Fahrenheit?
Around that, yeah, a massive jump, and it unlocked incredible technological change.
How did that early iron smelting even work? It sounds complicated.
It was sophisticated for the time, a two-step process, basically. First, you needed to get the oxygen out of the iron or iron oxide.
Reduction.
Right. Heat it to maybe 1,500 Fahrenheit with carbon charcoal. The carbon grabs the oxygen, makes carbon monoxide, leaves you with relatively pure, spongy iron.
Okay, step one.
Step two. Heat that iron hotter, maybe 2,000 Fahrenheit or more. Not hot enough to melt the iron itself, that's closer to 2,800 F, but hot enough to melt the impurities.
So the impurities melt and run off.
Exactly. They form slag, which you can separate.
Yeah.
This precise temperature control was absolutely key to getting usable iron.
And it wasn't just metalworking, was it? Pottery, too.
Definitely. The evolution from basic fired clay to complex glazes mirrors this mastery of heat.
Glazes are like glass.
Essentially, yes. Glass-like particles that melt at a lower temperature than the clay itself. They fuse onto the surface.
Making the pot waterproof.
And decorative. It transformed a basic commodity into, well, practical art, another case of temperature-enabling transformation.
So how did people even start measuring these crucial temperatures accurately? Before the 1600s, it was just feeling hot or cold, right?
Pretty much qualitative, yeah. But there were early glimmers. Way back, people like Philo of Byzantium, Hero of Alexandria. They noticed gases expand and contract with heat.
Leading to thermoscopes.
Exactly. Not thermometers yet, no scale, but devices that showed thermal changes, the first step.
Then came Galileo and Santorio in Italy.
Right. Santorio is key. He actually put a scale on a thermoscope. That's arguably the first real thermometer.
And he tried to measure body temperature.
Systematically, yes. His medical theories might seem odd now, but the act of measuring body temperature quantitatively, that was a huge leap for medicine.
Even though Galileo had his troubles, Florence stayed a scientific hub.
It did, leading to the Accademia del Cimento around 1657, a whole group dedicated to improving thermometers.
Standardizing them.
Trying to, yeah. Documenting glass-blowing techniques, comparing scales, laying the groundwork for reliable measurement across Europe.
Okay, fast forward. Understanding heat itself. Count Rumford. Cans.
Yeah, Benjamin Thompson, later Count Rumford. He noticed the intense heat generated just by friction when boring cannon barrels.
And this made him doubt the old theory, caloric fluid.
Exactly. The idea that heat was some invisible fluid flowing around. Rumford thought, no, this heat seems limitless as long as the boring continues. It must be a form of motion. Internal vibrations in the material.
Like sound.
He made that analogy, yeah. Both generated, both dissipated. A revolutionary idea, rejecting caloric theory based on observation.
Though some of his other ideas were less successful.
Yes. Some later attempts to explain things like racial differences using ideas about heat rays seem pretty misguided now, but his core insight about heat as motion was spot on.
Then Sadi Carnot, steam engines. That feels crucial.
Absolutely pivotal. Early 1820s. Carnot's figured out the efficiency of an engine, how much work you get from heat, depends only on the temperature difference.
Between the hot part and the cold part.
Precisely. The boiler and the condenser. Hot source, cold sink. He compared it to a water wheel. The height difference determines the power. Same idea for heat engines, but with temperature difference, a fundamental limit.
And this leads to the laws of thermodynamics.
Directly. The first law comes shortly after Carnot. Basically, energy conservation. Heat is a form of energy. Total energy is constant, it just changes form.
Work done is heat in minus heat out.
Essentially, yes. Then Rudolf Clausius tackled the why. Why can't you convert all the heat to work? Why does heat always flow from hot to cold?
Entropy.
He introduced the concept of entropy, linked it to order and disorder. Spontaneous processes increase entropy, move towards disorder. Second law.
Energy of the universe is constant. Entropy tends to increase.
His concise summary, yeah. A fundamental arrow of time.
And the third law, Nernst.
Hermann Nernst refined it further. As you approach absolute zero temperature, entropy approaches a minimum, essentially zero, perfect order.
Absolute zero being
Yeah.
the coldest possible temperature.
Theoretically, yes, the point where all molecular motion stops. Minus 273.15 Celsius, or 0 Kelvin, average kinetic energy is zero.
And this molecular motion idea explains the gas laws. Boyle, Charles, Gay-Lussac.
Beautifully. Higher temperature means faster molecules, hitting the walls harder and more often, higher pressure.
A Gay-Lussac's experiment expanding gas into a vacuum without cooling. That argued against caloric fluid too, right?
It did. If heat was a fluid just spreading out, you'd expect it to cool. It didn't, not significantly.
But sometimes expanding gas does cool. Joule-Thomson effect.
Right, but that's different. In that case, the gas is doing work pushing against external pressure as it expands. It uses up some internal energy, so it cools. Expansion into a vacuum does no external work. Subtle difference, important implication.
So by the early 20th century, caloric fluid was out, energy was in.
Pretty much. Energy, its forms, its transformations, that became the unifying theme, which was crucial for understanding the huge timescales needed for geology and evolution.
Right, let's talk Earth's history. Big temperature changes there, uniformitarianism.
Yeah, the shift led by Charles Lyell, away from thinking Earth was shaped by sudden catastrophes.
Like Noah's flood.
For example, towards gradual processes, erosion, sedimentation, uplift, acting over immense time, slow change, big results. Lyell heavily influenced Darwin.
And Louis Agassiz. Glaciers, erratic boulders.
Agassiz tackled those weird, out-of-place boulders. His big idea, radical at the time, was giant ice sheets. glaciers covering continents, carrying rocks far from their origin.
Ice ages.
He championed the idea, providing evidence like rock striations, moraines, convinced people that vast ice ages were real.
And what caused them? Orbital changes. Adhammer, Kroll.
Adamar first suggested orbital variations in the 1840s, but got the mechanism wrong. James Kroll, a self-taught Scot later in the 19th century, developed it properly. Linked ice ages to cycles in Earth's orbit and tilt.
Then Milankovitch refined it.
Hugely. Early 20th century, Mouton Milankovitch meticulously calculated 3 key cycles.
The whopper.
Precession, yeah, about 22,000 years.
That's good shape.
Eccentricity varies over roughly 100,000 years.
And the tilt angle.
Obliquity, about 41,000 years. These Milankovitch cycles are now seen as the main pacemaker for long-term ice age cycles.
And we know about past climates from ice cores.
Incredible archives. Drill down into ice sheets in Greenland and Antarctica. You get layers going back hundreds of thousands of years. Annual layers. Like tree rings.
Sometimes, yeah. They show snowfall, dust levels indicating wind, volcanic ash layers, and, crucially, trapped air bubbles.
Samples of ancient air.
Exactly. Measure the CO2, methane, reconstruct past temperatures in atmosphere. The Vostok core in Antarctica goes back, over 400,000 years? An amazing record.
Does the ice core data match the Milankovitch cycles?
The long-term trends match remarkably well, but there's a wrinkle. The ice cores, especially from Greenland, show really abrupt, fast changes, big temperature swings, maybe 15, 20 degrees Fahrenheit, happening in just decades.
Decades. That's way too fast for orbital cycles.
Way too fast. The Younger Dryas cold snap, about 11,000 years ago, right at the end of the last ice age, is the classic example. A sudden, sharp return to cold conditions.
So what could cause such rapid shifts?
The leading idea involves the oceans, specifically the massive conveyor belt currents that move heat around the globe.
Wally Brooker's work.
Wallace Brooker was central to developing this idea, building on earlier stuff, even Ben Franklin noticing the Gulf Stream's influence. How could the conveyor belt cause the Younger Dryas?
The theory is the huge North American ice sheet melted, creating a giant freshwater lake, Lake Agassiz.
Right.
Suddenly, a new outlet opened, maybe the St. Lawrence River. A massive flood of fresh water poured into the North Atlantic.
And that mattered because
It diluted the salty surface water, made it less dense. This might have shut down or slowed the formation of deep, cold water that drives the Atlantic part of the conveyor.
stopping the heat transport northward.
Exactly. Leading to abrupt cooling in the North Atlantic region, like Greenland, while maybe causing other changes elsewhere. It's complex.
We see similar ocean-atmosphere links today, right?
El Niño?
A perfect example. Warming in the equatorial Pacific, but it messes with weather patterns globally. Remember the 97-98 El Niño?
Vaguely. Big news.
Huge impacts. Floods, mudslides, droughts all over the world. Shows how connected these systems are.
Which brings us to the greenhouse effect. How does that work, basically? Think of an actual greenhouse. Glass lets sunlight in, warms the inside. The inside radiates heat back out, but at longer wavelengths, infrared. The glass traps some of that infrared heat.
Okay, so Earth's atmosphere acts like the glass.
Sort of. Sunlight comes through, warms the surface. Earth radiates infrared back out. Certain gases in the atmosphere, greenhouse gases, absorb that outgoing infrared.
Which gases?
Main ones are water vapor, carbon dioxide, CO2, methane. They absorb infrared, then re-radiate it, some back down towards Earth. Traps heat, warms the planet. Without it, Earth would be freezing.
Who figured this out?
Fourier made the greenhouse analogy early on. John Tyndall, mid-19th century, experimentally showed which gases trapped heat, CO2, watered it.
And Arrhenius calculated potential warming.
Svante Arrhenius, late 19th century, did the first calculation. If CO2 doubled, how much warming? His estimate was surprisingly close to modern ones. Pretty prescient.
Then in the 20th century, people started worrying about actual CO2 increases.
Yeah, Roger Revelle, Charles David Keeling, mid-century. Keeling started the direct atmospheric CO2 measurements at Mauna Loa, showed it was steadily rising, linked it to burning fossil fuels.
And now we have the IPCC.
The Intergovernmental Panel on Climate Change synthesizes all the research. Their reports show clear warming trends, strong consensus on human causation, and project future increases.
Other complications? Feedback effects.
Oh yes, warming melts ice, reducing reflectivity, causing more warming. Warmer air holds more water vapor, itself a greenhouse gas. Clouds are complex, some cool, some warm. Forests change, it's intricate.
And the missing carbon sink.
Yeah, we know how much CO2 we emit. We know how much stays in the atmosphere. Where does the rest go? Oceans absorb a lot, plants take up some. But the budget doesn't quite balance perfectly. Still an active research area.
Okay, let's dive deep. Literally, deep ocean exploration. Pickard's bathyscaphe.
Alvin. Those technologies opened up the abyss and led to some stunning discoveries about temperature and life.
Hydrothermal vents.
Exactly. Found along mid-ocean ridges, tectonic boundaries, vents spewing super hot mineral-rich water from inside the Earth.
Oh, hot.
Some black smokers are hundreds of degrees Fahrenheit, way above surface boiling point, but the immense pressure keeps it liquid.
And life thrives there, in that heat.
Astonishingly, yes. Whole ecosystems, giant tube worms, Pompeii worms, they don't use sunlight.
Chemosynthesis?
Right. They use chemical energy from the vent fluids, sulfides, methane to make food, totally independent of the sun.
Are there even more extreme life forms? Microbes?
Oh, yeah. Hyperthermophiles, bacteria, archaea, things like Pyrolobus fumariae, Pyrococcus furiosus. Their optimal growth temperature is above boiling point at sea level.
Wow. How's that possible?
Again, deep-sea pressure prevents boiling. It suggests maybe a vast, deep biosphere of heat-loving microbes inside Earth's crust. And there are acid lovers, too. Acidophiles. Life finds a way in extremes.
This leads to wild ideas, doesn't it? Like snowball Earth.
The hypothesis that Earth might have frozen over completely, or almost completely, a few times in the deep past.
And vents could have been refuges.
Exactly. If the surface was ice-covered, deep-sea vents could have kept life going. Even smaller events show the impact Krakatoa erupting in 1883 cooled the globe for years from the ash.
There was another ancient warming event, too. PTM?
Paleocene-Eocene thermal maximum, about 56 million years ago. Rapid, intense warming. One theory involves massive releases of methane, a potent greenhouse gas from ocean sediments, caused big extinctions.
Is snowball Earth widely accepted?
The basic idea of severe past glaciations is, but whether it was a hard snowball totally frozen or a slush ball with some open water near the equator, that's still debated. Evidence exists for both sides. How early complex life survived is tied to that debate.
Could life have actually started at these vents?
It's a compelling hypothesis. Jack Corliss was a big proponent. Vents offer chemical energy, minerals, and protection from surface hazards like UV radiation and early asteroid impacts. A potential cradle for life.
Speaking of impacts, the dinosaur extinction. KPG boundary.
The Alvarez hypothesis. Strong evidence now. Global iridium layer, the Chicxulub crater, points to a massive asteroid impact.
And the temperature changes killed them.
Likely a combination of effects. Initial heat blast, then impact winter dust, blocking sunlight, causing extreme cold, collapsing food chains. Then maybe longer-term greenhouse warming from released gases. Rapid, catastrophic temperature shifts.
Earth's early history was even hotter, right? Bombardment.
Oh, yes. The formation period. Constant impacts. Generated immense heat. Drove volcanism, helped start plate tectonics. Very challenging conditions for life to emerge. High surface temps, maybe impact-induced nuclear winters. A tough start.
Does this suggest life might exist elsewhere?
Europa, Jupiter's moon, is a top candidate. Strong evidence for a subsurface liquid water ocean.
Kept warm by tidal forces.
Exactly. And if there's a rocky seafloor, maybe it has hydrothermal vents like Earth's, a potential habitat. Lake Vostok, under the Antarctic ice, is maybe an Earth analog, a huge subglacial lake, possibly geothermally heated. The Galileo mission gave us great data on Europa. Now, let's look up the sun, our main heat source.
By far right. 10,000 times more heat than from inside Earth. Gamo's book, Birth and Death of the Sun.
A classic popular science book explains our evolving understanding. We see the surface, the photosphere, about 5,800 Kelvin, hot, but the real action is deep inside.
Sunspots are cooler areas, right?
Yeah, appear darker. But the big 19th century puzzle was the sun's age. Geology and evolution needed billions of years.
And known energy sources couldn't explain that, like burning coal.
Not even close. Chemical burning would exhaust the sun's fuel way too quickly. It was a major scientific crisis. How could the sun shine for so long?
Until nuclear fusion was understood.
Exactly. Hydrogen fusing into helium in the core. Driven by incredible temperature and pressure, Einstein's Imsiat showed mass could convert to enormous energy.
Eddington proposed this.
Sir Arthur Eddington was a key figure championing fusion as the sun's power source. And incredibly, we can even check the core temperature.
So, we can't put a thermometer there.
Neutrinos. Tiny, elusive particles produced in the fusion reactions. They fly straight out of the core, barely interacting with anything.
Messengers from the core.
Precisely. They reach us in minutes. And by measuring their flow, scientists determined the core temperature, 15.7 million Kelvin, with stunning accuracy, better than 1%.
That's amazing. How can neutrinos tell us the temperature?
Their production rate is extremely sensitive to temperature. A slight change in core temp drastically changes how many neutrinos are made. This sensitivity comes from quantum mechanics and nuclear physics, understanding how nuclei interact at those energies. Rutherford's early work probing the atom was foundational.
Fusion's different from fission, right?
Right.
Power plants use fission?
Fission splits heavy nuclei like uranium. Fusion combines light nuclei like hydrogen in the sun. Fusion needs incredibly high temperatures to overcome the electrical repulsion between protons.
And bigger stars can fuse heavier elements.
Yes, they get hotter cores, fuse helium to carbon, then heavier elements up to iron. When they die, massive stars explode as supernovae.
Dispersing those heavy elements.
Exactly, making them available for future stars and planets, like ours. Supernovae also release huge bursts of neutrinos.
Carrying temperature information.
From the collapsing core, which reaches billions of degrees. Supernova 1987A was a landmark neutrino detector, saw the burst hours before the light arrived. Confirmed theories about stellar collapse.
Let's go back even further. Early universe, Big Bang.
Incredibly hot and dense initially. As it expanded, it cooled. A key moment was about 300,000 years after the start.
Recombination.
Yes, universe cooled to about 3,000 Kelvin. Cool enough for electrons and protons to combine into neutral hydrogen atoms. Before that, it was a hot plasma soup. This was the last time matter and radiation were tightly coupled in thermal equilibrium.
And the radiation from that era is still around.
The cosmic microwave background, CMBR, the afterglow of the Big Bang. As the universe expanded, this light got stretched to microwave wavelengths.
It is temperature now.
About 3 degrees Kelvin. Incredibly cold, almost absolute zero. Discovered accidentally by Penzias and Wilson in the 60s. Huge evidence for the Big Bang.
And our current understanding of cosmology.
Yeah.
Flat universe, dark matter.
All built on this thermal history. We think the universe is geometrically flat. Most matter is mysterious dark matter. Expansion is accelerating due to dark energy or a cosmological constant. Big puzzles remain.
Theories like inflation try to explain things.
Inflation and other ideas like the ekpyrotic universe model try to explain why the universe is so smooth and uniform on large scales, as seen in the CMBR. It's a very active field. Still lots of wonder. Okay, one more big area, quantum mechanics. Seems abstract, but it connects deeply to temperature.
How so? It governs the very small.
It does, but its effects become obvious, even macroscopic, often at very low temperatures, and it underpins modern tech.
There was that race to liquefy gases in the 19th century.
A huge scientific effort, driven by curiosity, competition. Pixtet, Kayetet, Dewar with his vacuum flask, Wroblewski-Olszewski, pushing colder and colder.
Until Kamerlingh-Onnes liquefied helium.
The last holdout. Helium liquefies around 4.2 Kelvin, incredibly cold. Onnes achieved it in 1908, and helium itself was found on the sun before Earth. Ramsay isolated it later.
And Onnes' work led to?
A complete surprise, superconductivity. He was measuring the electrical resistance of mercury cooled by liquid helium. At 4.19 Kelvin, the resistance vanished. Completely.
Zero resistance.
Zero, a purely quantum effect. Revolutionary. Quantum ideas were new then, facing resistance. Einstein helped push them forward. His work explaining the specific heat of solids, like diamond, at low temps. He argued atomic vibrations must be quantized, not continuous, matched experiments where classical physics fail.
And then Bohr's atom model.
Quantized orbits.
Explain spectral lines perfectly, electrons jumping between discrete energy levels, more quantum winds. Pauli's exclusion principle explained the periodic table, why atoms behave chemically as they do. So, low temperatures are the quantum realm.
In many ways, yes. Quantum weirdness becomes more apparent. Discontinuities, not smooth changes. Think superfluidity in helium-4 below about 2 Kelvin. Flows with zero viscosity.
Bose-Einstein condensates.
Another ultra-low temperature phenomenon predicted by Bose and Einstein. Get atoms cold enough, they merge into a single quantum state, behaving as one wave. Achieved in labs now. Pure quantum mechanics on a visible scale. Helium-3 behaves differently, again due to quantum rules. It was a radical shift in physics.
Einstein even worked on refrigerators. Seems unexpected.
Yeah, he and Leo Szilard, after reading about accidents with toxic refrigerants like sulfur dioxide.
Which were common then.
Yes, they designed a safer fridge with no moving seals. Used a liquid sodium-potassium alloy pump, driven electromagnetically. Clever design. Didn't make him rich, though. He also worked on a hearing aid later. Practical side, too.
Quantum mechanics impacts stars, too. Chandrasekhar.
Subramanian Chandrasekhar. His theoretical work showed massive stars can't all end as white dwarfs. There's a mass limit.
The Chandrasekhar limit.
Right. Above that limit, electron pressure, a quantum effect, isn't enough to stop gravitational collapse, especially when you include relativity. Leads to neutron stars, black holes. Eddington initially resisted this idea, famously, but Chandra was right. Quantum mechanics governs stellar death, too.
It's amazing how these fields connect. Temperature seems to be a thread running through so many breakthroughs.
Absolutely. Superconductivity at low temps, Rutherford figuring out the nucleus with particle scattering, the CMBR telling us the universe's temperature history, life thriving at scorching hydrothermal vents, often unexpected discoveries linked by temperature.
It highlights that interplay between theory and experiment, doesn't it? Constantly pushing understanding forward.
Exactly. Challenging assumptions, revealing surprising connections. That's the process of science.
So wrapping up this deep dive, it's just incredible the range we've covered, all tied together by temperature.
From our own bodies to the rise of civilization with fire, the laws of physics, Earth's long climate story, the sun's furnace, the quantum world.
All the way to the Big Bang and the potential for life elsewhere. Temperature really is this powerful lens, isn't it, for understanding almost everything.
It truly is, and it illuminates the history of science itself, how we came to understand these things.
Maybe that's what's special about us. Not necessarily our place in the cosmos, which might be quite ordinary.
But our ability to understand it, to unravel these secrets, partly by studying something as basic as temperature.
Yeah, maybe that capacity for understanding, that curiosity, is what makes our existence here so remarkable, even in a vast universe.
That's a fascinating thought to end on. Gives you perspective. Our drive to know, to measure, to figure things out.
Yeah.
Perhaps that's the extraordinary part.
Absolutely. It certainly gives you a lot to think about and hopefully encourages everyone listening to maybe explore some of these ideas further. The universe is packed with wonders, and temperature holds keys to so many of them.